Grade 11, Mechanics, Session 4. From the last session, we looked at Newton's first and Newton's second law. If you guys remember that one, what we're saying is that something will stay where it is unless we push it, pull it, lift it, or do something to it. Or something will keep moving, like you're on a bicycle, as long as your force forward is the same, until you put in an external force like the brakes, or, for example, the road surface changes. Because if you're going down a tar road and suddenly you're going to sand, we all know what happens under those circumstances. We normally end up in the sand, because there's an external force that's being applied to us. That is the reason if you've been down some of the very steep roads, specifically Van Rhenen's Pass down to KZN, KwaZulu-Natal, you'll see on the side of the road in the very steep areas, they've got a big special sign, and there's a huge piece of road going off straight and a big sand area. That's called an arrestor bed. What it's there for is it's to absorb the energy of a truck that loses its brakes. Those are things we'll get into in grade 12, but essentially what has happened is that the surface has changed between the two. Okay? Now, there's a section I want you to just briefly talk about Newton's third law, just so that we can finish that element off. Just to read Newton's third law, it says here, Newton's third law states that when object A exerts a force on object B simultaneously exerts the oppositely directed force of equal magnitude on object A. Pretty much, the simpler version of that is that for every action force, let's say, there is an equal and opposite reaction force. Well, okay. Let's break that down into basic English. Once again, we know that this has a mass and it has a weight, mg. If I put this on the table, what is happening? The weight is still there. The table is sharing the weight. It's feeling the weight. It's feeling this on top, isn't it? If we come along and we put this on top, it's feeling two of these. All this law is saying is that this table is pushing back with the same force that it feels. Well, let's just think about if it wasn't. If this force on top was more than this could push back with, this would be sinking down, wouldn't it? It would be almost like foam. We'd be sinking into it until the force was able to keep us up. If the table was pushing back with more force, this would start floating off, wouldn't it? Well, we don't see that. So what have we got here? We've got a situation, and all we really think about is, think of it in terms of you must have seen these huge wedding cakes and things like that, and I don't know, you get the baking shows and things. Let's say, for example, we've got this cake. We've got a cake underneath, and I've left a gap between the two. Okay. And let's say these cakes are on a table over there. Okay? No, they're not floating. Let's say the first cake is 5 kilos, 10 kilos, and 15 kilograms. Okay? And they want to know, what are the contact forces? What are the forces between? What is the total force exerted by one thing on the other thing? Let's call this cake A, cake B, and cake C. Let us find the force exerted by cake B on cake C. So what do? We go to the interface between the two. We put ourselves there and we say, right, put yourself in there and say, right, if I was lying there, how much force do I have to push up with? Hang on. You have to push up 15 kilograms as a bench press, don't you? That's what you have to push up. So that's the contact mass. Let's change it to forces. 5 kilograms is going to be, this is why I wish they'd have left it as 10, but 5 times 9.8 is going to be, so this one here, the top cake, is 49 newtons. 10 kilograms is 98 newtons. 15 times 9.8, 15 times 9.8 is going to be 147 newtons. All I've done is I've changed the mass to be the weight. So I'm going to have to lie there and push up over here like that. I'm going to have to push up with what? 98 plus 49. Isn't that so? I'm going to have to push up with 98 plus 49, 147. Okay? What is the contact force, or what is the force that C is exerting on the table? Or what is the opposite reaction, the equal and opposite reaction? The table, what is the table pushing back with? Well, what is the table holding up? If I had to lie under there, what must I push back with? I must push back with 147, 98, and 49. So I've got to push back with 294. What am I holding up? I'm holding up 30 kilograms, aren't I? So I'm holding 30 kilograms above me, which is that. So in essence, this whole situation is extremely logical, because what do? We go and we ask ourselves that question. We ask ourselves the question, what must I push back with? Because that is the reaction. The one to the other one is its reaction, right? Essentially, that goes back to the normal force that we speak of. Now, let's go forward off this topic and let's deal with a topic that shouldn't really cause confusion, because friction. Before we move ahead with this, let's examine what friction is. It's nothing special. You rub your hands together when it's cold, they start to get warm. That is the friction effect generating heat, right? Have any of you perhaps felt, let's say for example, there's one, on some of the scooters, the smaller scooters, you've got that little back pedal you push back on and it pushes a brake onto it. Have you ever felt how hot that gets? A car's brakes. Sometimes in winter, if the car's been braking heavily, you can actually see the heat coming off it. Why? It's this. It's things rubbing together. And guess what? The rougher they are, the more it's going to generate heat, isn't it? If I took my hand and I rubbed it against sandpaper, I'm very soon going to be feeling the heat of that one. Similarly, if we come off on grass, we slide. Okay? Yep, you still get a grassy, but you slide. Come off on tar, and it literally slides, but it rips us to pieces. There's more friction between us and that, because it's rougher, in inverted commas. So let's just think of friction as being the roughness, a measure of the roughness, how a surface can be. Well, let's think, what can we have that's got nothing? Ice. Ice on ice, right? If you've ever had the fortune of skiing or ice skating, you know just how slippery it can be when you put a very, very machined, flat, smooth piece of metal onto ice or snow. Even sometimes with shoes, you can't stand up on it. There's no friction between them. The reason being is essentially, if you were wearing that, you could run on the spot and you're not going to move, because there's no friction that lets you move. Think about it. It's logical. So let's call it ice. So ice is zero. You're going to see them saying things like a frictionless surface. The moment you see the word frictionless, it means you can ignore friction in that calculation or in whatever they're asking you about that problem. However, not many things are completely frictionless. So yes, oil. There is friction between a concrete floor, a box, and oil. There is some, but it's not as much as if I took the oil away. Then let's take sandpaper. You can imagine, if now you've got something sitting on sandpaper, it becomes more difficult to slide it. Think about a plastic crate, right, that's on a driveway, on the tar road. You want to move it, or on dirt road. As you push, okay, you feel the friction acting against you. Because what does the friction want to do? The friction wants to stop you from moving. So the first thing about friction that we have to put down is that, what does it do? It always acts against direction. It acts against the direction of movement. So if we are pushing this on the surface, I'm pushing it, it's not moving. Why? Because there's friction between there and there. Think about that crate again. You've got it on the tar, and you push the crate. Then the dog comes along and hops in the crate. It gets more difficult to push, doesn't it? Then all of a sudden, one of your friends decides to hop in the crate and says, push me. It gets more difficult to push. What is it saying? It's saying the more weight I pack on here, the greater the friction acting against me. Similarly, if I took my crate off the tar and put it on sand, it gets even worse. So you can see that the weight has got to do with it, and the different surfaces have got to do with it, right? So we can think of friction as the roughness. And what do we measure it with? In physics, we've got, it's called the coefficient of friction. And it's given a type mu. That's what we call it, a Greek letter mu. A lot of the stuff in physics is Greek because the Greeks were involved in a lot of it. It's mu. Now, what do we do with this mu? Well, it's a number. The number varies between 0 is frictionless and 1, which basically is the same as saying the two are stuck together. Okay? In other words, it's very rough. Okay? Well, we said that tells us something about the roughness of the surface, the mu, right? And we'll go through mu s and mu k, the static and the kinetic friction. But so that mu, the higher it is, the rougher it is. Let's say the rougher it is, right? The closer we're getting towards frictionless. Okay. Now, the next thing we said that the amount of friction that we felt when we were pushing was linked to the weight. So we can say frictional force is proportional to Fw. What does it mean? It means the more directly proportional means if that goes up, that goes up. If that goes down, then that goes down. That's essentially what directly proportional means. The one goes up, the other goes up. If the one goes down, the other goes down. Okay? Indirect, one goes up, the other goes down. One goes down, the other goes up. So let's have a look at these two. We now say that, okay, what are we saying? We're saying they're directly proportional. The heavier, the more the friction against me. The final formula for friction, for those of you who know, to get rid of that, you put in a constant of proportionality. In this case here, the constant of proportionality is mu. That's what you have to remember. Force of friction is mu, coefficient of friction, times the weight acting down. So the frictional force is a percentage, it's a fraction of the weight. That's really what it's about. Just before we move on and start solving these, you will see mu s and mu k. Let's explain those out in quite simple terms. Mu s, static friction. Static, not moving. What does it mean? Let's go back to our example of a crate and your friend's in the crate and you push, and all of a sudden it starts to move and then it feels as if it gets easier to keep it moving. That is the difference between these two. Mu s is more, it's actually more than mu k. So if mu s was, let us say, 0.4, mu k might be equal to 0.35, let's say. It means that when it's moving, the frictional force drops. It is less of a force to keep it moving. But generally, they're going to give us one or the other in the problems. They might, in the theory part, ask about the difference between the two or whatever, but that's quite a simple explanation. Just think about it logically. It's not maths. Static, I've got a coefficient of friction. It drops when I start to move. That's what we see in reality. That's what real life is about. Now, how do we go about problems when they give us a frictional force? Well, what we do is, like we said, in any physics problem, we do a drawing. That's what we do. What are we going to do is we're going to say, right, we have got an object over here. It's got a mass of, I just want to leave it with my 10 kilos there. What do? We put in Fw equal to 98 newtons, m times g. Now we say, right, they now tell us mu is equal to let's say 0.35. The first thing we do when we're given mu is we go along and we say force of friction is equal to mu times F normal. Now I've got to go and put my F normal in here. You can see there I used FW, right? It's actually F normal. I'm going to show you why in a few seconds. F normal. In this case, F normal is equal to FW, okay? Because that's the formula there, because F normal could be less than Fw, depending on if we had other forces acting, lifting it up or pulling it down. We'll do that with a roller going across the thing now. So F normal is acting up. F normal, in this case, is equal to 98 newtons. That is Newton's third law. This pushes down on here, this pushes back with exactly the same amount. So therefore, friction is going to be 0.35 times 98 newtons. And we go ahead and we work that out. Because we put our friction in, we say 0.35 times 98 is equal to 34.3 newtons. But now, here's the problem. We don't know at this point. We say it's a force, but which way is it going? Well, let's just look at this. Can you see the block over here? It's not going down the slope, but if I lift it, it moves, right? What is keeping it on the slope is the force of friction. So the force of friction always acts opposite to the direction of motion. Right. Let us say that I put a force in over there at T, right? Now this is the question we always ask ourselves. What does that block want to do? First, let's say there's no friction. Where does the block want to go? The block wants to go that way, doesn't it? It wants to start moving this way because I've got a force. Then I go and I say, right, block wants to move that way, so friction must be 34.3 newtons that way. I always put the maximum value of the friction in there. So what have we got? We say the block wants to move that way. So let us say if I pull with 34.3 newtons, the block is not going to move Because what's happening, I am in equilibrium, aren't I? If I pull this way with 34.3 newtons, and friction is that way with 34.3 newtons, I'm in equilibrium. It's me with my 34.3 and 34.3. I am not moving. I'm in equilibrium. If I, however, pull with, let's say, for example, we pull over here with 50 newtons. Aha! Now I must up that one to 50 newtons over there. Do we now, what do? We look and see if we've got an F net. Have we? Yes, we have. We've got an F net here because we are pulling that way with more than the other way. Just looking horizontal. So our F net in this case is 50 minus 34.8. Oh, my bad, sorry, 34.3. 34.3, which is going to be equal to 50 minus 34.3 is equal to what, 15.7 newtons. And what do we do? What do we do when we see that? F net, MA straight away. So we go and we say, right, F net equals MA, and F net is 15.7 is equal to mass 10 times A, therefore A is 1.57 meters per second squared to the right. So you can see again that the F net is going to come in, but now we're going to be, the next session we're going to start dealing with friction in a little more depth, okay? Because this is the problems that we need to resolve. Is essentially the question we're going to be asking is, which way is friction acting? That's the nub of this. That's the key. Which way is friction going to act? Is it going to act helping us in a way, keeping it on something, or is it going to act against us if we're trying to move something? So we'll ask that question in the next session, and we'll answer it. At the end of the sessions on this, we're going to do the problems, as I've said, on sloping surfaces, linked with pulleys and things like that. But we've got to get through this friction thing first. So in the next session, we'll do that. And